Hello and welcome. This will be a video on how to teach exponents for math teachers and just in general any math educator. It will not necessarily be a video for students to watch themselves. I'm going to go fairly quickly through topics and just give a higher level explanation. This will more be for educators to understand how to teach the topic, how to explain it, what best practices there are with communicating the ideas, and also any tips or tricks that I find very helpful that might not be standard when dealing with exponents. I have been a math tutor for 5 years, and I have a bachelor's in higher secondary math education. So I feel like I have a pretty decent understanding of the topic. Not everything, for sure, but I have a lot of tips and tricks, things that I would like to pass on and see if other people can benefit from them. So, one of the first things I would think to cover with exponents is just a general introduction to them. Even if you're teaching a higher level class where the students are a bit older and they sort of know notation, don't necessarily expect that they know exactly what the concept is about. If you're dealing anything with exponents, I would almost always start with exponents imply repeated multiplication. That is a huge thing to hammer home. 3 to the power 4 is 3 times 3 times 3 times 3. And some people will give you just weird looks for that, but it is very handy to understand. What is a base? What is an exponent? What are they doing? How do I write that out? How do I think about that? That is just a huge component to why a lot of students don't necessarily get always what's going on here. So 3 to the power 4, 3 times 3 times 3 times 3. I might even index them and say 1, 2, 3, 4, just so students can see that, oh, okay, you take the same base as many times as you need it, and in this case, it's 4 times because of that exponent. 1, 2, 3, 4. Leaving that up there as an example, I would almost always start with the numerical values first as well, 3 and 4, or 2 and 6, or 3 and 9, or whatever. Because anytime you add variables in, it gets more confusing. Give students something very concrete to latch onto first, and then go into the more abstract terms, like 3 to the power of x, or maybe a little bit as a better start, x to the power of 3. They've more than likely seen something like this. Again, same basic rules. You keep the same base and you multiply it 3 times. 1, 2, 3. And indexing it out might help. Very straightforward, very nice, cool. And then the weird one. 3 to the power of x. We don't know what x is. So how do we index it? Well, it's a little bit harder to think about, but we know it's going to be 3 and 3 and 3 and 3 and dot 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 out to some number of times. We don't necessarily know how many times. In fact, it could be fewer than this. X could be 1, x could be 2, x could be a million. But we know when we write something like this that we're multiplying 3 by itself some number of times. And it's a little bit hard to display that without, a lot of movement involved in the diagram saying, oh, it could be once, could be twice, could be 3 times, could be 4 times. Who knows? So, if you're introducing exponents, going through something like this can be incredibly helpful to just get everybody on the same page to understand we are doing multiplication, we are using bases, we are using exponents, then try to introduce higher level concepts. So the next thing that probably is going to come up is exponent rules, how to combine things with exponents. There are a few major ones. The first one is almost always x to the power of a times x to the power of b equals x to the power of a plus b. Very standard, straightforward thing. You might even understand it, but let's give it a shot at explaining why this works the way it does. I would almost never use variables to do this. It's just going to get more complicated. Instead, pick something like 3 to the power of 2 times 3 to the power of 4. give students something concrete to latch onto. What we said before is totally applicable to this. In fact, you can basically cover this one up and just say, okay, well, what's 3 squared? By the rule we just used, 3 squared is 3 times 3, twice, index of 2. Then you can take that 3 to the 4th and say, okay, well, what's that? 1, 2, 3, 4, 3 times 3 times 3 times 3. These are 2 groups. We have a group here, and we have a group here. Maybe I shouldn't do that in red. I'm going to try and make this as readable as possible. However, this multiplication that was in the middle of them is still in the middle of them. That has not changed. How many 3's are there? 1, 2, 3, 4, 5, 6. So this would be 3 to the power of 6. The parentheses here don't, they're not changing anything. It's just a group of 3 6s, 6 3's. So this would just be 3 to the power of 6, which ultimately is, if you want to put it as simply as possible, 2 plus 4. That gets you 6. The nice thing with an example like this is it sort of visually tells students, like, okay, I'm doing a group, I'm doing another group, and I'm squishing them together. That's where the 6 comes from. That's intuitively why you're doing addition when you're actually doing multiplication. And that's what trips people up most often, is differentiating the 2 factors, differentiating why am I doing multiplication and then somehow doing addition. The next rule, of course, is the opposite to the previous one. Say x to the a over x to the b equals x to the a minus b. It might be incredibly obvious as to why this works, but let's give it a shot using numbers. 3 to the power of 4 over 3 to the power of... let's make this a little bit bigger, shall we? I like larger examples, that way you can sort of concretely tell what's coming out of what. Because if you do things like 1 and 2 and 4 and 3 or 4 and 2, then numbers start to repeat themselves a little bit and it gets confusing. So, by the rule of breaking things up, 3 to the power of 5 is 1, 2, 3, 4, 5. 5 3's. 3 to the power of 2, 3 times 3. As for what happens here, division is great, especially when it's only over multiplication on both sides, because things can cancel out in the top and the bottom. 3 over 3 is just 1. Another 3 over 3 is just 1. Problem is there's nothing else. You can't cancel 3's that don't exist here in this spot. So what's left is always a 1. What that then gives us is 3 times 3 times 3 over 1, which is, of course, 27 over 1, or just 27. So this ultimately results in that, if you know how to combine them. Oh, and I guess I should state more accurately with the rule. This is just 3 to the 3rd power. And you can do that as 5 minus 2. Again, that should always work, because you have 5 objects on top, and you are taking away 2 of them. You're canceling them out as long as they're exactly the same, which they should be for the rule to work. That's why you need the same base on the top and the bottom. So yeah, canceling things out in this case looks like subtraction. They're not exactly the same, but they do look similar enough that it works out pretty well. Another very common rule is 3 to their... let's just use x. X to the power of a to the power of b equals x to the power of a times b. Yeah, not incredibly impossible to explain. Switch back to green here. Using concrete numbers, 3 to the power of, say, 2 to the power of, say, 3. Again, you can use whatever base you want here. It might be a little confusing. if using the same 3 in multiple places, so maybe I would use a 4 here. 4 squared to the power of 3. The way I try to think of this is that 4 squared you want to join as like a single object in your head. Treat this as one thing. It's getting put to the power of 3. Well, what does that mean? You have 3 of them. That's going to be 4 squared, and 4 squared. And remember, exponents join through multiplication. You don't have to calculate all of these separately. You can use exponent rules, again, to make this faster. When multiplying things with the same base, you add the exponents, which is going to be 2 plus 2 plus 2, 4 to the power of 6. So ultimately, this results in 4 to the 6th power, which is just 2 times 3. And that will, again, always work, because you're always going to take this smaller number, 2 in this case, and go, okay, how many 2's do I have? 3 of them. Or in this case, how many A's do I have? Well, I have B number of A's. See how that's just more confusing to conceptualize? But having B number of A's is just B times A, or A times B. And another very common thing at slightly higher exponents levels is negative exponents. Say x to the negative a is 1 over x to the power of a. This one's a little bit strange. And the reasoning for it can be best found by the subtraction rule, or knowing the subtraction rule. So let's say we have x to the 3rd and x to the 5th in this case. Similar to that other rule we did for division, that other example we did, but sort of flipped this time. What happens here? We have x times x times x, and 1, 2, 3, 4, 5. I'm using a variable this time just to simplify it. But again, I would stick to numbers most often when doing very introductory basic examples. So what happens here? They still cancel. Cancel those, cancel those, cancel those. There's a 1, but it's on top. 1 over x squared. Squared, of course, because there's 2 of them. Which is a little strange. That doesn't look like a normal, output of an exponent rule. Normally, they're just a base and an exponent. This is under the fraction. And that happens because if we do the subtraction rule here and actually do that, that's x to the negative 2nd. 3 minus 5. You have to do them in order. Subtraction, order always matters. A lot more so than other cases. And then that implies this and this are the same thing. They mean the same value because we could get them to be equal to each other. So negative exponents, when you see them, just mean they're on the bottom of their corresponding fraction. As a quick little aside here, very often I'll see people do this. We'll do like x to the negative 2nd equals 1 over x to the negative 2nd. They'll just inherently try to keep the negative around because they think that like it's connected to it, like it still has to be negative. No, by flipping it, by doing the reciprocal, you're dealing with the negative. So that's sort of the point of doing that. That's why this is now a positive 2, or more often than not, we just don't even write anything. It is a positive exponent now because it got flipped. And one of the last rules is how to deal with a fractional exponent. X to the power of a over b is the b root of x to the power of a, which is very strange and unintuitive. There's a decent way to explain it. But first off, let's just go through an example quickly because I want to show you something. X to the power of, say, 1/3. Let's not do 1/3. Let's do 2/3. Again, 1 can get a little confusing because it often just disappears and you don't know what you're looking at anymore. Having both numbers concrete is very helpful. What this ultimately will look like if you break it up by the multiplication rule. So let's again quickly cover that x to the a to the b equals x to the a times b. You can also do this in reverse. You can also split up a fraction. 2 over 3 is equal to 2 times 1/3. That's the same thing. So this 2/3 is actually 2 times 1 over 3. Well, that's two separate objects. That's this a over b right here. What can we do with that? We can split it. So this whole thing is equivalent to x to the second to the 1/3. Two separate things joined by multiplication, and we just put them as separate exponents. One's to the x, and then one is to the whole thing overall. The order doesn't really matter. You can also do it as x to the 1/3 squared. I just don't really prefer it that way. So the squared exponent here is a perfectly normal squared exponent. Nothing fancy happens with it. The 1/3, on the other hand, that's a weird one. Exponents are not normally fractions. How we deal with that, we introduce the radical, which I'll explain momentarily. But that becomes the third root. That 3 becomes part of the radical because it's the weird part of the exponent. And then the x squared just stays as an x squared. Totally normal. So it's the third root of x squared. As for why fractions turn into radicals, the best way I've found to explain it is by thinking of this as sort of a continuum. You have, say, let's use 3 as a base. 3, let's go 0, 1, 2, -1, -2. 3 to the power of 0 will get you 1. 3 to the power of 1 will get you 3. 3 to the power of 2 will get you 9, and so on and so forth, getting larger exponentially. 3 to the power of -1 will get you 1/3, as we explained previously. 3 to the power of -2 will get you 1/9. So, where do fractions fit into this? Well, they can't be negative, so we can't put them in this area. They're definitely not very big, so we can't put them in this area. Oh, sorry. Yeah, right up to there. All these numbers are still -2. They've got to fit somewhere in here, somewhere between 0 and 1. Well, that's ultimately anything between 1 and 3 in this case. How do we get smaller than 3 without guaranteeing that we will never get smaller than 1? Radicals. The square root of that 3, or the third root, or the fourth root, or the fifth root, or anything like that, will infinitely approach 1, but it'll never reach it because 1 to any power is never anything other than 1. So you have to be slightly bigger than 1 in order to ever reach any new value, 3 in our case. But radicals work perfectly for that. It's not a great explanation, but that's generally the why I think of, radicals have to exist somewhere in here because this is a continuum. You can get every one of these numbers, including everything between 3 and 1. Some common mistakes I see when learning these exponent rules is people try to overgeneralize them. So they'll say, oh yeah, 3 to the a plus 3 to the b is 3 to the a plus b. Because they learned the rule one way. It should probably work this way too, right? But unfortunately not. You have to remind people that this is multiplication. Remember, this is a set of things being multiplied. This is a set of things being multiplied. That's not multiplication. The issue becomes then, because it's not all multiplication, you cannot collect it together. It's going to be separate things, which means this will not work the way you want it to. Again, addition causes problems. Addition is more complicated than multiplication generally. In the same vein, I very often see 3 to the a times 3 to the b is 3 to the a times b. Because that just generally makes sense, right? It's multiplication, you multiply. But unfortunately not. This one's a little bit tougher to get a hold of because people very often will just say, you're multiplying. Like, you're multiplying them. Why not just multiply them? That's literally the symbol that's written here. And it'll take a good bit of work to say that not necessarily. This is multiplication. This is multiplication. This is multiplication. It's all multiplication. So it's like putting groups of blocks together. I don't know of a better way to explain it. In all honesty, that's how I visualize a lot of things. You have a block here and a block here, and you're putting them together. And you don't multiply blocks when you put blocks together. You add groups of blocks together. So this whole thing overall is one big addition problem, which is why that turns out to be addition. It's combining things. Those are two very common mistakes. Another thing I see is the simpler rule, 3 to the A to the B. Well, sometimes A plus B, just because they're going too fast. They mix up a rule, and they combine this previous rule and try to extrapolate it to this one. Or they just totally miss an operation. They're like, oh, I meant to do multiplication there. That's fine. This is one of the more common phrases that I ended up repeating. Was when you have a power to another power, you multiply, not add. So, again, those key phrases that I talked about in my educational philosophy video will come in handy for stuff like this, where you just see the same mistakes over and over again, get quick, very punctual ways to remind students to fix them. Here are a few other quick things I wanted to cover. Explaining the zero power, that anything to the power of 0 will always get you 1. Of course, you can just take it as a rule and assume that that's always true, but it's always a little strange as to why 1? Why not 0? Anything, let's say 3 to the 4th over 3 to the 4th. Any base that's the same on the top and the bottom, you can subtract the exponents. What if they're the same exponents, though? 3 to the 4th is a number. It's calculatable. 3 to the 4th is that same number. So you can do it two different ways here. 3 to the 4th, 3 to the 4th. 4 minus 4 is just 0. Written out by our traditional exponent rules, the subtraction rule, 4 minus 4 gets you 0. But like we was kind of just saying, this is a number over the same number. That, hopefully, is easily understood as just 1. Any number over itself is 1. That's a quick explanation of this, and the 3 here does not matter. You could replace 3 with any number you would like, any variable you would like. If you have the same thing over itself, you'll always get 1. You will also always get an exponent of 0, because the exponents will completely cancel themselves out by subtraction. It's good when clarifying canceling out, if you're doing it to 0, if you're doing it to 1 by division. A few other things here. These are somewhat smaller exponent rules that you don't see come up quite as often, but they are incredibly useful when they do come up. X times y, in this case 2 different bases, all being put to a power using parentheses. That power can be distributed into there. It's not quite distribution, but it's pretty close. So this would turn into x to the a times y to the a. The exact same thing can happen over division. You can have a exponent put to x to the a over y to the a, which is great. And this is another key indicator of if you can do it over multiplication, if you only change that multiplication to division, you can probably still do it. Those are very classic rules, barring a few maybe weird examples. And another very good thing to realize is that most exponent rules apply to radicals in some form or fashion. This can also be the square root of x times the square root of y. Sort of like saying that one big thing overall can be put to 2 separate things, like this a and this a. Except now it's one radical being put to 2 separate radicals. And by exactly the same logic, square root of x over square root of y, that just works because this rule works. And explaining these, I actually don't think I have a very good trick for them. So you may just have to take them along a little bit of faith. And here is just a general rundown of all of the exponent rules that we talked about. You've got your two very basic ones that I always think of as linked together. Multiplication results in addition, and division results in subtraction. Multiplying power to power, you multiply the exponents together. Negative exponents are the reciprocal, they end up getting flipped. And two things to a power, you can split the power, and two things being divided to a power, you can split the power. One thing to keep in mind for all of these rules is that if you ever get stuck on like, why isn't a problem working as correctly as it should, maybe you're not going in this direction. Maybe you're going in this direction. Every rule here can be used one way or to go backwards. Maybe instead of simplifying something down to a more smaller exponent, you need to expand it out into its larger version. We did that rule when explaining the radical one, which I don't have here. Quickly put that. X to the power of a over b equals the b root of x to the power of a. When we did this one, we used the multiplication rule to state that, okay, 2/3 can be 2 times 1 over 3. Instead of being simpler, we needed to break it apart, and that's where we could do the more solid explanation of it. Sorry for the bright white screen, but if you haven't seen Desmos, it's a fantastic graphing software. I would probably introduce the concept of at least of exponential growth and decay. Maybe not necessarily a full lesson if you don't need it, maybe not even necessarily a graphing lesson if you don't need it, but at least show students this concept is related to other things. In fact, very directly related to how graphing them works. So you could have things like x squared, which of course is just a regular parabola, but you can also have x to the third. And explain like, okay, well, this is what happens when you have negatives to the third power. They become negative again, which is why this is going down and this is going up. This pattern will continue infinitely with the fourth, and then x to the fifth, and then yada, yada, yada. This is maybe not the most exciting bit of it. They probably have already seen some basics of quadratics. But what about when you put 2 to the power of x? That looks a little bit different. It's not symmetric, for one thing. And it does go infinitely in all directions. Show that this is a form of exponential growth. Time progresses to the right. It's usually how I think of it. Growth progresses to the right on the x-axis. If you start out with negative time, it's very, very, very small. And it gets a little bigger. A little bit bigger. Hits 1 eventually. Gets bigger, bigger, huge. Ginormous. Goes up off to infinity very quickly. We're not even to 10 yet, and we're off the graph. So this is a form of exponential growth. You're doing that because it's 2 to the first power, to the second power, to the third power, to the fourth power, and explain why that gets massive very, very, very quickly. Because it's multiplication happening over and over and over and over again very quickly. You can also then explain how to do exponential decay and say that, okay, well, this base is 1/2. 1/2 times 1/2 is 1/4. That's smaller. That's not bigger. So as we progress in time here, you're not going to be getting bigger. You're going to be getting smaller. Which then, of course, implies if you do negative numbers here, these get huge very quickly. And that's because if you take a fraction and flip it, as a negative exponent should do, it's no longer a very small fraction. It's just whatever number the denominator was. Like 1 over 20, but it just becomes 20. Or, whatever the case is. That's why this gets huge, because these negatives are actually flipping it to be, instead of very, very negative, to be very, very positive. And of course, these numbers just continue to get smaller and smaller and smaller, because fractions times a fraction is always smaller. Those are the things I would cover with any exponent lesson. Again, it just has to be that. You don't have to go into super detail of how to graph them and how to understand them and why, you have to know all of this perfectly. It's just an introduction to this concept relates to another concept. Once they've seen that, hopefully it sticks. And when this comes up in the future, they might say, oh, yeah, that was that thing with exponents. If they don't remember it perfectly, that's fine. But it's at least an introduction to these things should be connected in your head. And one of the final and more complicated things in doing exponents is solving exponential equations, which can get very annoying. You can have something like 3 to the power of x equals 3 to the power of 2x minus 1, or something to this effect. The reason this can be annoying is because the bases aren't always the same. If the bases are the same, then it's a very nice, simple little thing to do, as long as it's one base equaling a single other base. There is a logarithmic way to explain why this is the way it is. If you're curious, I might do something on logs in the future. But for now, we can simply say that the 3's essentially just cancel each other out. All that's going to happen here, x equals 2x minus 1. And then from there, that's very basic algebra. Just do minus x plus 1, and you get 1 equals x, and then yada, yada, yada. But the key component to this is because the bases are the same, the exponents have to equal each other. If the bases are not the same, things get quite a bit more complicated, unfortunately. You can do something to the effect of 8 to the power of like 2x minus 1 equals like 2 to the power of like 3x plus 4. I actually don't know if this is going to work out or not. Just made this up off the top of my head. But the idea is that you always want to be dealing with the larger of the two bases. And that is because exponents can take large numbers and write them as smaller numbers. That's the best way to do it. Taking the 8, bringing it down to a 2, really cool, nice, awesome, we can do that. Taking the 2 up to an 8, you're going to have to introduce other things into the problem, and it's not going to work. Not nicely. So 8, you have to sort of do a separate problem. You can think of as 8 is 2 to what exponent? Of course, if you don't know logarithms, you just have to figure it out. But it shouldn't be all too incredibly impossible. It's 2 to the third power. 2 times 2 times 2, that's 8. So because of this here, 8 can be entirely rewritten as 2 to the third power. Well, this 8 can become 2 to the third power. To the power of, let me put that in red, 2x minus 1 equals 2 to the 3x plus 4. Well, what rule do we apply here? Power to a power. You multiply. Notably, this should be in parentheses. You do have to distribute the 3 to both parts of this. It's a little messy in there. This would end up being 2 to the power of 6x minus 3 equals 2 to the power of 3x plus 4, and I'm not necessarily going to solve out the rest of this, but you now have it such that 2 cancels. The bases cancel. So you have exponent equals exponent, traditional algebra. The hardest bit, definitely, is getting the bases to be the same, because sometimes you end up with bases like 1 over 24. That's not going to work. 1 over 27 to a power equals 3 to some power. You can get this to work. This is simply going to be 3 to the negative third power as a base. That will get you 1 over 27. But it's very hard to see that right off the bat, where you're like, I don't know where this fraction's coming from. How do I flip a fraction? You have to recall back to that previous exponent rule and know that that's what a negative exponent does. I would quickly like to go about how to cover a larger problem like this, and in fact there are multiple ways to do so. There are multiple ways to solve it. So you can try to simplify everything in here first. That's probably the better way. But you could also use the rule of taking this exponent and applying it to absolutely everything in here. The 27, everything, the squared, the third, the z, the negative 2, the 4, the 3, absolutely everything. Both ways are fairly acceptable. So let's try and do the simplification method first. 3 and 27 will simplify to simply be 1 over 9, yeah? Yeah, it's going to take me a second to think of this. 4 minus 2 is going to be x squared. Notably, it's a positive x squared. This is another common mistake I see people make, is putting it on the bottom, because they're like, oh, well, I don't know, maybe it ended up on the bottom. But if you end up with a positive exponent here, it ends up on top. Positive 2. This, on the other hand, negative 2 minus 3 is going to be y to the negative fifth, which is confusing because I have seen some people do y to the negative fifth down here on the bottom. The problem with that is it is a positive 5, and that's because negative exponents are the reciprocal. When you calculate something like this and do subtraction, negative 2 minus 3, you're always going to get the variable on top. It's just always going to be like y to the negative fifth on the top of the fraction. But the easiest way to think of that and to simplify that is if you get a negative, it does end up on the bottom, but it's a positive now, because that's what negatives do. They flip to the bottom. And of course, z is just z. Nothing changed there. All of this would be to the negative second power, and then you could apply here as 1 to the negative second over x to the negative fourth, multiplying. Remember, it's good to clarify when you do 2 with 2 which operation you're using, again, for simplicity's sake. Negative 2 times 2 is negative 4. The 1 exponent on this z makes this z to the negative second, 9 to the negative second, and y to the negative 10th. The interesting bit here is absolutely everything flips. So this would be, the one just goes away, that doesn't really matter. This would be 9 squared is 81, y to the 10th, over x to the fourth, z to the second. So that's one way of doing it. You could, however, also apply the negative 2 to everything first. Or in fact, you could also just apply the negative to everything first and flip the whole thing and then apply the 2. In fact, that might be easier. But let's just apply the negative 2. 3 to the negative second, x to the negative eighth, y to the fourth, z to the negative second, 27 to the negative second, x to the negative fourth, y to the negative sixth. All right, because everything's negative, or most of it's negative, we can flip everything. 27 squared, 3 squared, x to the fourth, x to the fifth, y to the sixth, and y to the fourth are both still on top, and z to the second is on the bottom. This will result in the x's canceling. I'm going to need to figure out what this is quickly. 729. Fourth and fifth. 4 minus 5 is negative 1, but remember that just means the x ends up here on the bottom. This is going to be y to the 10th and z squared. Why are our x's different? And this is the case where you might need to troubleshoot some things. Because that was an 8. That was not a 5. 4 minus 8, negative 4, so the 4 ends up on the bottom. There we go. And then this, I'm assuming, is 81, which I can just quickly check here. 729 divided by 9 is, in fact, 81. So, cool. And that ends up being exactly the same as what we had down here. It was probably a little difficult to follow that, in all honesty, but you get the idea behind it. That you can simplify first, or you can distribute the exponent first. Distributing the exponent is probably harder, but it's equally as valid. Some students may very much appreciate knowing how to do the simpler way. Some students may completely latch on to one method and never want to give it up, even if it's significantly harder. If the math is correct, the math is correct. I would say let them do it. But, of course, there is also the issue of timing and pacing and how much work you can actually get done in a certain amount of time. It's a balancing act. But ultimately, math is math. Just for some last-minute reminders, try to be consistent with terminology, and try to use the correct terminology even if you're saying something else. So, like, very often I would say, like, oh, we're doing 3 with blah, blah, blah. 3 is the base. I would explain that and say the base, which in this case is 3, does blah, 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 blah. Be consistent with the wording that you're using. Or the exponents here, which are 4 and 5, do blah, 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 blah. Try to use the same words over and over and over again. Clarify that these rules are only for exponents. That was something with the mistakes that we went over. Some people try to generalize these rules to a whole bunch of other things because they look the same, or because they're not 100% sure which operations they were used for. Clarify specifically these are only for exponents in these specific cases, in this specific setup with these specific operations when you are teaching them. Avoid using the same numbers in examples, as I said. Students really have to know where these numbers are coming from and what they are doing. If there's like 3 different 3s in your problem and they're all doing different things, and 3 ends up here and it's also the number of things there are and it's also part of the answer, that's going to be incredibly confusing. Try to make examples where each number has its individual place, does something different, and so students can see why the numbers work the way they do. Give gentle reminders for common mistakes. Try to have a list of phrases, quick, to the point, snappy catchphrases that will tell students, that's the error that you're looking for. That's a very difficult one to give advice for, because students can make all sorts of mistakes. So, but be very gentle with saying that, okay, well, let's think about it this way, or let's look over this stuff. And then, we went over this one in one of the previous slides. Rules can be used forward and backward to expand or simplify. Very, very handy when dealing with more complex problems. Thank you very much for watching. This has been a full explanation on exponents and the ways to go about teaching them, my own personal tips and tricks. If anyone catches an error, please leave a comment. I'm almost certain I made at least 1 or 2. Or if something's unreadable, or some small detail I said incorrectly, I'm open to criticisms, and I'm open to improving this video in the future. I don't necessarily have a topic in mind that I might go into next. I'll take some requests. Maybe factoring, maybe graphing from parent functions, maybe logarithms. I don't necessarily know. Subscribe for more math topic explainers in the future. Perhaps request one. And stay up to date. Thank you so much for watching.